Okay. Hello, everyone. Good morning, good night, good evening, wherever you happen to be right now. It's my pleasure to welcome all of you to day three of the main conference for Micro 53. We'll start today with a keynote talk by Bobbie Manne, who I'm very happy to and honored to introduce today. Bobbie is a computer architect. She's been in the industry for a while now, working across a range of companies from Compaq, Intel, AMD, Cavium on processor designs and architecture, and is now a principal hardware engineer in the Azure Hardware Systems and Infrastructure Group at Microsoft, where she's also looking at larger scale systems than the processors. And we hope if you get inspired today about something that I think our community hopefully will grab a larger mind share of, which is sustainability and not just performance. So I'm looking forward to your talk, Bobbie.
Thank you, Matan. And good morning, everyone, or good afternoon or good evening, depending on where you are. So as Matan said, my name is Bobbie Manne. I'm a principal hardware engineer at Microsoft. So I just want to state that the opinions I state in this talk are mine and not necessarily those of Microsoft. Okay, so let's get on to our talk, which is about architecting a sustainable planet. If I can get it to move. Okay, there we go. So general outline of the talk, I'm going to give a brief background on carbon emissions and some perspective on that. We're going to go through some data center history and analysis of carbon emissions in the data center. I'm going to go over some ideas on sustainability and some innovative solutions, and then conclude the talk. So couple of things to keep in mind here. One, I'm going to be talking primarily about carbon and data center, but sustainability, of course, includes many different areas. And then the second thing is that if you start diving into this field, what you find is that you'll find different numbers from different people, depending on what assumptions they made, what pieces that they computed, and what they included in their calculation. So in this talk, the general idea should be not necessarily to focus on a number, but focus on the trends and the relationships in those trends. Okay, as I said, there are many, many facets to sustainability. So if you're talking about design for sustainability, you can include any of these pieces on this pinwheel. I'm going to focus on a few of these, but you can have topics ranging from carbon emissions to water security to environmental justice, for instance. So again, as I said, I'm going to focus on carbon and data centers here, but there's a wide range of topics. So first of all, carbon emissions, global warming, it is real, and companies are listening. So global warming is a planet-sized challenge, and global warming is related to the amount of carbon emissions that are being produced. If you take a look at the carbon emissions over the last 200 years, there's been an exponential rise in carbon emissions, and most of it is really related to energy consumption. So now when we talk about energy consumption, let's bring it down to the data center and take a look at the energy consumption in a data center. So data centers used about 205 terawatt hours of electricity used. Now, it's really hard for me to understand these numbers and put it in perspective to something that I can relate to. So what that means is that data centers, the electricity in the data centers used was equivalent to about 31 million cars being driven per 1 year, or the amount of electricity generated by 31,300 wind turbines, or the amount of carbon absorbed by about 190 million acres of forest land, which by the way is bigger than the state of Texas, or 145 million metric tons of carbon. So this will give you some equivalence and a way to think about the problem. Now, companies have been paying attention, and you'll see headlines all over the place. Google, Facebook, Microsoft, Amazon, Apple, all these companies have been thinking about carbon for the last decade at least, and are aggressively attacking this problem. But you also have companies like Walmart now talking about it. So data centers are really the backbone of the internet. And we all access the internet on a daily basis, in fact, on the Zoom call. So the little things that we do on the internet all add up. So let's take a look at an example of what I mean. So looking at Facebook, their numbers show in their sustainability report that the average monthly user uses about 0.1 kilograms of carbon, a tiny amount. which is equivalent to driving your car about a quarter mile. But Facebook has about 2.38 billion users. When you combine the two, their carbon per year is 252,000 metric tons. Even that number is actually pretty small because about 86% of their carbon comes from renewable resources. So if it wasn't for the renewable sources, that number would be significantly higher. Now, these numbers for Facebook really include only the carbon associated with running their data centers and their offices. But we should also look at the devices and the carbon associated with the devices that we use and the power in those devices when we access the internet. So here's another example, this time with Netflix. And in this case, these numbers include not just the power associated with streaming the data in the data center from the data center, but also the power associated with the devices that are being used to watch these Netflix videos, whether it be a cell phone or a TV. That's why you see a range of numbers here. Now, it takes about 0.12 to 0.24 kilowatt hours for 1 hour of Netflix video, which is about 0.2 to 0.4 miles within your car. But in a single day, 165 million hours of Netflix videos are watched, which then comes to a total of 5.2 to 10.4 million metric tons of carbon generated per year by Netflix alone. And that's the equivalent of 1.1 to 2.2 million cars driven for that year. So when we talk about data centers and we talk about the internet, it's really death by a billion swipes. Every little thing adds up. And here's a pinwheel of a number of other applications that use data centers and the internet. And what you can see is that there's millions and millions of little tiny things happening all over the place that accumulate to these numbers. So Satya Nadella stated that the goal should be we should have a cloud for everyone on every device. And the current world population as of last month was 7.8 billion individuals. And about 60% of them, or 4.6 billion of them, are internet users, which means there's a remaining 40% that are not. Now, our goal should be to bring all these folks onto the internet because there's certainly great economic advantages to doing so. And what that states is that our data center usage is going to continue to go up. So let's take a step back and think about a historical perspective. If you read articles about sustainability 10, maybe 15 years ago, there were all these projections about how data centers are going to be consuming some large percentage of the world's electricity, somewhere between 3 and 8%. But what the numbers have shown is that hasn't come to fruition, and primarily because of the efficiencies of scale that we've seen over the last decade. So here's some numbers. On the y-axis is the terawatt hours once again, and on the x-axis is the trend over the last 10 years or so and some projections. What we've seen is that there's been a 2x increase in the number of users, a 12x increase in the amount of traffic, but only a 6% increase in the energy use for these data centers. And primarily because traditional people have been moving from traditional data centers onto the cloud and onto hyperscale. So, and these large data centers have significant efficiencies. So let's take a look at a qualitative example of how this is being achieved. So here is a dot that represents the kilogram carbon per used for traditional data centers. And in hyperscale data centers, we can have multi-tenancy and dynamic allocation, so through virtualization and being able to scale up or scale down based on the user's needs. So traditional data centers have a utilization around 15% or 15%, and hyperscale have utilizations in the 50 or 50% range or higher. So we can get better use out of the data centers and out of the equipment. In addition, we've seen significant improvements in terms of hardware efficiency over the last decade. As computer architects, we've seen multi-core, more and more cores go onto a processor, and the power budget doesn't necessarily keep increasing proportionally. So what this means is from a data center perspective, we can have more users in the data center for the same power budget of 1 megawatt or 10 megawatts or whatever the number happens to be. Third, data centers, especially hyperscale centers, have done an excellent job of lowering their PUE or power usage effectiveness. This number represents basically how much overhead you have for every unit of energy that goes to compute. So a PUE of 2.0 means that for every unit of compute, I have 1 unit of overhead, whether that goes into cooling or power delivery inefficiencies, et cetera. A PUE of 1.0 is the best that I can achieve, which means there's no overhead. And generally, hyperscale data centers are now seeing PUEs of around 1.1. And finally, because of the large scale of these data centers, quite a number of them have been able to purchase zero emission sources. So when you combine all these features, what you see is that hyperscale data centers are about 90% or more efficient than the traditional enterprise data centers. And this is how we've been able to keep the power used in these data centers down in the last 10 years. So let me just show you a couple of examples here. On the left-hand side, I'm showing for Google, basically their PUE for 12 months, trailing 12 months starting in the first quarter of 2020. And for their data centers, you can see PUE ranges from about 1.07 to 1.15. So really good numbers. On the right-hand side, I'm showing a chart that was generated by the IT folks at Etsy. Now, Etsy is basically an online marketplace for people who make crafts. So these are not individuals that you think of who would care about data center efficiency. But what Etsy has noted is that they expect their users to go up, and they wanted to make sure that their carbon footprint was staying as low as possible. So they transitioned, or in the process of transitioning, from their current data center onto the Google Cloud. And their current data center has a PUE of basically 1.4, and the Google Cloud has a PUE of 1.1. And by transitioning, they were able to lower their energy consumption and improve their carbon footprint. So what this says at a high level is that outside of just the IT companies, customers are starting to care, even companies like Etsy. So what we know so far is that we expect data centers to continue to grow, and hyperscale data centers have provided some significant efficiencies. So let's now look at the data center from top down and see where the carbon goes. So before I do that, let's take a look at hyperscale data centers in particular and look at the growth. So what we see is that they're continuing to grow, and about 38% of them are located in the United States. Now, going one step lower, let's take a look at hyperscale data centers for Microsoft. Here's a chart that shows the different Azure regions we have with Microsoft. And this chart is about 8 months old or so. So in fact, the number of Azure regions have increased, I think beyond the 53. But what you can see is that we have regions all over the world, and a significant number of them are located in the United States. Let's take it one step down again. Here is the data center picture from a few years ago. And these data centers are enormous. They take up vast amounts of land, and there's a lot of building on them and a lot of construction work. In fact, what you can see is that here's the parking lot for that data center to give you some perspective of just how big this data center is. Now, that was a few years ago. This is a picture of that same data center now. In fact, it's located in that far corner of this bigger complex. And this is one data center complex for one company. So what this says is that when we talk about carbon emissions in data centers, so far I only mentioned the carbon emissions associated with using the data center. But when we build these data centers, you have to think about the full all the components of this complex, which is the buildings that have to be constructed, the equipment that has to go into the data center, and the carbon associated with using that equipment in the data center. So why should we care about the buildings and how do they contribute? Well, as Jocelyn Timperley stated, if the cement industry were a country, it would be the third largest emitter of carbon in the world. So cement alone is accounting for about 5 to 8% of total carbon emissions in the world. So we need to start considering the materials that are used to build the buildings, in addition to the components that go in there and also how we use them. So why do we care about the carbon within the components? So here's a visual of how we should think about data center equipment lifecycle. So when you are building the components that go into the data center, the servers, the racks, the clusters, everything else, we have to first think about extracting that material and refining it, which requires energy. Then we transport it over to a manufacturing site where things like CPUs, GPUs, DRAM, networking equipment, cooling equipment, batteries, everything is manufactured. It's once again transported into an assembly site where it's assembled into a rack or a server and so forth, transported again to the data center where it's used, and then finally transported again at the end of life where it is recycled. Every single step of the way involves energy and emissions. So the way to conceptualize this is that in data center equipment, there is what's referred to as embodied carbon, which is the carbon that's already built into that particular component or structure that is as part of the manufacturing process. And then there is the use carbon, which is the carbon associated with using that particular component or server or anything else. And both these things matter. So stepping back again, let's take a look at what the distribution of the carbon associated with the building, the carbon associated with the component embodied carbon, and the carbon associated with using those components, how these three pieces fit together. Now, this is really a back of the envelope type of construct. So I made some assumptions about the size of the building that we're going to need for a 1 megawatt data center, use some equipment information from Dell and so forth. So the key here is not to necessarily run away with the specific numbers, but to look at the trends. So let's say I built a 1 megawatt data center and I'm looking at the embodied carbon in the equipment, the use case carbon in the equipment, and also the carbon that was required to make the building. The distribution looks as follows. In the first year, 13% went to the building, 36% went to the carbon in the equipment, and then 51% went to the use of that equipment. But we don't keep buildings or servers around for 1 year. In fact, usually the lifetime of a server is around 4 years. So if you take a look at a 4-year life cycle for the server, the distribution changes. The building carbon becomes a smaller portion, and as does the embodied carbon, because now we've used this server for 4 years as opposed to 1 year. And then if you take a look at the life cycle of the building, which is around 20 years or more, the carbon associated with the building shrinks even further. And because we had to go through 5 revisions of servers in that building in that 20 years, the distribution of embodied to use case carbon remains approximately the same. So the takeaway from this is that we have to look at the life cycle of the components, how long they're used, and that can change the distributions. The other thing is that the amount of carbon associated in the use case can actually change based on the type of fuel you're using and the carbon intensity of the electricity that's coming in. So in these examples, I assumed a very carbon intensive power source, which is coal, to generate the electricity. But if the electricity is generated by other means, these numbers will diminish. So not all electricity is created equal. The carbon intensity can change anywhere from wind being in the low tens of grams of carbon per kilowatt hour to coal being around 700 to 900 grams of carbon per kilowatt hour. In addition, where the data center is located can have implications about the carbon intensity of the electricity coming in. So we have to take a look at all these pieces. Now let's go back to that 1 megawatt data center and look at the picture for one server life cycle of 4 years. Now, if I assume that my electricity is coming from coal, most of my carbon will go to the electricity that in the use case carbon. And if I assume that my electricity is coming from what's referred to as a Nordic mix, which is around 300 grams of carbon per kilowatt hour, use case is still dominant, but now the embodied carbon is 1/3 of the total carbon emissions. If I now assume wind, the use case carbon nearly disappears, and now what dominates is the embodied carbon. So all these things have to be taken into consideration. Now, one question that people can ask is, well, how much is the electricity generated by all these renewable sources? And the answer is a lot these days. So the cost of solar and the cost of wind have gone down dramatically in the last 10 years. So now renewable power is becoming much more economically feasible, and a lot of data centers are relying on it. But there's a problem with renewable power, which is that it's intermittent. If the sun isn't shining or if the wind isn't blowing, you're not going to necessarily be able to get your electricity from renewable power. So we have to think about, if you're going to run a data center, how we demand shape what we run on the data center, the when, where, and how we run the jobs in order to take advantage of the variability in renewable power. So here's an example of an energy mix from California for 3 days earlier this year, starting in April 19th. And what I show is that the combination of where the electricity came from, starting at 12:01 on Sunday and ending basically at 11:55 on Tuesday. So across the 3 days, what you can see is that in the middle of the day, solar power is a big component, and as is wind. And these contributions are reducing the amount of imports that that particular operator has to bring in. Now, imports are shown on the top, and at the end of the day, when the sun sets, the imports increase. And this cycle tends to repeat over the 3 days. Now, this is just the amount of electricity that was used in the combination of the sources for the electricity. Now, if I overlay the carbon intensity on top of this, which is measured in megaton of carbon per hour, you can see that the carbon intensity goes down when we have solar energy during the middle of the days, and then it goes up when we bring in the imports from other states. So what this means is that if we can plan our data center scheduling of jobs for low carbon intensity time periods, we can reduce the carbon footprint of the jobs and of the data centers. So something to note here is that there's actually like a 7x variability in the carbon intensity. And so there's large potential for shaping our demand to take advantage of this. So here's an example of a project that was done at Microsoft. Microsoft has these things called a hackathon every summer, and a group of individuals came together and said, okay, what would happen if we could shift workloads from the Azure Batch service in a data center in the Netherlands? And what they found is that for workloads that are less than 24 hours in duration, they were able to reduce their carbon, basically provide about 11% carbon savings for those jobs. And for jobs that are less than 5 hours, they got about a 10 to 27% carbon savings. So this is feasible and there is potential for doing this, but we have to look at other complexities, such as if the length of the job is such that it runs for days and days and days, we might not be able to take advantage of the shifting carbon intensities during the period of a day. In addition, we have to look at the complexities of how jobs are coming into the data center. So here's an example of the number of VM requests per hour in a particular zone. And this is averaged out by day of the week over the course of 5 weeks. And what you can see is that there's large variability in the number of jobs that come in to the data center. Now, we have to then consider the variability in the jobs in addition to the variability in the carbon intensity of the power sources. So what I did was I overlaid here some real carbon intensity numbers, once again from the California source, for a couple of weeks ago, basically. And there are times when the carbon intensity and the jobs line up well to reduce the carbon footprint, and there are times when they don't. For example, here, the jobs line up well where the carbon intensity is low and the amount of jobs coming in is high. And here, the carbon intensity is high along with the number of jobs being high. So this is not necessarily a good point. So when we think about trying to shift workloads in time in order to take advantage of carbon intensity, we have to think about the amount of workloads coming into the data centers, the amount of workloads that could be coming in the next few minutes or hours. So we have to think about all these different complex interactions in order to optimize for this case. So I'm not going to go into details. I talked in the last set of slides about shifting in terms of time, but you can also consider shifting in terms of location. Here's a carbon intensity map for Europe for a particular time of day. And what you can see is that if you're going to run a job now, it would be better to run it in France, where the carbon intensity is low, than maybe in Italy. So the takeaways from the last set of slides about trying to work with this demand shifting and carbon intensity is that there's a number of different metrics that we have to juggle. The application needs, the customer requirements, the mix of the renewables, how much hardware is available, because there's only so many servers in the data center, and we might not be able to shift if there not enough hardware is available to run them. And then we also have to think about the fact that if you are moving to a data center with low carbon intensity, then you're leaving idle another data center and reducing its utilization, and you already paid the carbon tax there for the embodied carbon that's already in that other data center. So all these different factors have to be considered. Now, there's a number of different ideas that you can research in this area. The first thing is VM power estimation. It's really a non-trivial thing to figure out how much each VM is consuming in terms of power, and that's necessary to do this kinds of demand shaping. The demand shaping algorithm itself, how do we balance all these things? How do we predict the carbon intensity? Can we predict it over the course of a day? How about a course of a week? Also, how do we predict the job duration if the customer is not going to tell us? How do we then think about potentially checkpointing, either in software or hardware, these jobs so that we can suspend them for a period of time and then come back again when the carbon intensity is low? And then also, how do we think about writing applications that can be more delay tolerant so that we can play with these fluctuations better? So the last set of slides really talked about how we try to reduce the carbon intensity based on the use case carbon. But now let's talk about the embodied carbon. And specifically, I'm going to focus on sustainable silicon because numbers have shown that silicon tends to be one of the biggest contributors to embodied carbon. So here are some numbers out of TSMC. When you go and look at their TSMC sustainable report, they report out 14.1 million metric tons of carbon, and about 75% of their carbon footprint came from electricity and 25% from what's referred to as high global warming potential chemicals, such as perfluorocarbons, for instance. Now, you could argue that, hey, TSMC could also go to renewables and reduce the electricity, the carbon impact of their electricity use. And right now in 2019, about 7% of the electricity comes from renewable resources. But TSMC has also projected that by 2030, they will increase the renewable portion of their electricity, but the increase is only up to 25% of their total electricity consumption. What that means is that they're projecting to do better, but they will not completely eliminate the carbon emissions from electricity. So we have, as computer architects, taken advantage of all the benefits that we've gotten from the process shrinks that have occurred. We get significant power and performance benefits. For instance, going from 16 to 7 nanometer, we can reduce power by about 65% if we kept performance constant, or improve performance by 35% if we kept power constant. But the benefits we're getting are starting to diminish as we go from 7 to 5 nanometer and 5 to 3 nanometer and so forth. In addition, there's significant increase in cost and complexity. A 5 nanometer fab is quoted to cost about $5.4 billion. In addition, designing a SoC for a 5 nanometer process is expected to cost over $500 million. So we have to look at all these things when we think about, does it make sense to go to the next silicon manufacturing process? In addition, what TSMC has noted is that as the process gets more mature, it gets more energy efficient. So the way to read this chart is as follows. The red bar is the normalization point for all these other bars. And this is talking about the energy efficiency in the manufacturing process. We're not talking about energy efficiency in transistors or anything. This is the manufacturing process. Higher is better. So if you take a look at the first year of a process node and compare 7 nanometer to 16, 28, and 40 nanometer, what you see is that 7 nanometer was less efficient than the other process nodes in their first year of operation. If you look at 7 nanometer and compare it to the second and third year of operation, what you can see is that it's getting more and more efficient as it becomes more mature. If you compare, for instance, 16 nanometer in its fifth year of operation, is twice as efficient as 7 nanometer in its third year of operation. So what that says is that if it makes sense to stay at an older node, that node is more energy efficient in the manufacturing process of the wafer. Okay, so these are things that we need to consider when it comes to sustainability, because if it's more energy efficient, it also has a smaller carbon footprint. So what does this mean when we talk about building sustainable software? The key points are that we need to think about, sustainable hardware, I should say. The key points are we need to think about using it longer. We need to think about making the silicon cheaper in terms of carbon, and then also think about doing more with less components, okay, or increasing the utilization. So before we get into some ideas around this, let's step back and think about how hardware engineers think about processors and how VMs think about processors. So as architects, we think about a processor as being, let's say, 64 or more cores in the case of AMD, or coherent last level cache. It has 8 memory channels or 256 gig of memory. It's a dual socket system and so forth. We think of it as this monolithic chunk of silicon that has all these different components. In the data center, on the other hand, applications see their VM or their processor in their viewpoint as being a small number of cores, generally 2 or 4 virtual cores. Here's some data from a couple of zones out of Azure, and over 85% of VMs, or nearly 85% of VMs, are less than or equal to 4 virtual cores. In addition, most VMs are not using a ton of memory. 70% of VMs require less than 4 gigabytes of memory. So what this means is that although we see a processor as a single chunk, the VMs are really breaking it up into subcomponents. And what that means is that the whole system doesn't have to be perfect for it to be usable in the data center. So the key is, don't throw the baby out with the bathwater, and we should think about resilient hardware and software to support maybe imperfect hardware in the data center. So let's take a look at what this means. So first, we need to think about increasing usability of the hardware by adding spares or tolerating defects. Now, we already have spare DRAM rows. We already have spare, basically, SSD cells. And so this is not anything new, but we can think about adding spare cores so that if there is a defect, we can still continue to have a fully operational processor. And another idea would be to add spare capacity. Or we can make sure that the hardware and software is resilient enough such that we can work with a processor that mostly has 64 cores, but sometimes it'll have 56 cores or 61 cores. And the software and firmware stack can deal with that. The second thing is that once the processor lands in the data center, we might start detecting additional issues with the processor. So we need to think about detecting, isolating, and managing these faulty components in the processor itself. So we're thinking about graceful repair and recovery, such that if there is an issue with one VM, it doesn't bring down all the other VMs on the system, and we can gracefully isolate whatever the faulty component might be such that it's not used again in the future. Now, we could even think about things like maybe the component is only faulty in a particular range. For instance, a core might work just perfectly well up to, let's say, 3 gigahertz. But anything above that, it starts becoming flaky. So if that's the case, we can think about shunting the max frequency of that core down to 3 gigahertz and having the mechanisms in place to do that. The third thing we can think about is resource pooling and disaggregation. So we can pool SSDs, DRAMs, accelerators, such that they can be shared by multiple nodes in the rack or in the cluster. So there are two benefits to this. One, if there is any kind of failure, it can be tolerated better because there's a larger pool of components. And two, as we've shown, not every VM needs all these capabilities or needs all the capacity. Now we can share the resources better across more VMs and get more use out of the limited set of components. So the last thing is to manage feature updates. What happens is that in a data center, we don't have homogeneous processors or systems. It's not like we replace all the systems in the data center at one time. So within a data center, you have multiple generations of hardware. And if we can manage these feature updates such that maybe we can use older hardware to run applications built for newer hardware, or vice versa, what that means is that from a scheduling and allocation of VM perspective, we have a homogeneous data centers. And that allows better utilization inside the data centers. So we can achieve this via a software shim layer and our microcode that can emulate different kinds of characteristics. So another way we can think about the problem is to disaggregate the processor. So there are significant sustainability benefits to chiplets. Now, we spent the last probably 3 decades integrating more and more components in the processor that has given us benefits in terms of latency, and it probably also has been a good sustainable solution because we've replaced 2 chips with a single chip, for instance. But now we're getting to the point where things are getting complex enough that we might need to start thinking about breaking things up. So the sustainability in the concept of chiplets is that by taking the processor and breaking it up into subcomponents and designing each subcomponent in its own process technology, and making each subcomponent smaller, we will have less waste due to defects. We'll be able to increase the yield. We can use the optimal process for each subcomponent. And we can also have higher reuse on those components from generation to generation when they don't need to be shrunk to the next generation process node. So in this example, the IO hub can stay in 14 nanometer. We can bring it in from generation to generation. The cores are in 3 nanometer because we needed the performance improvements that provided. But the last level cache is in 5 nanometer because SRAM is expected not be able to have as good a density in 3 nanometer process node. So it stays in 5 nanometer. So these are different ways to think about the problem. And as noted, using older nodes also means more energy efficient um, process technology for those nodes. So in the last few slides, I provided a number of ideas, but none of these are really new to the architecture community. We talked about resilience and reliability. We talked about chiplets are actually in use in AMD processors. But what I'm now stating is that we should examine all these architectural decisions through the lens of sustainability. And by doing so, we can shape the decisions in different ways and by adding sustainability as part of the cost function. Okay, so far I've talked about ideas that are more evolutionary in nature, that work with the existing data centers or work with the existing hardware that we use in the data centers. But really now we should start thinking outside the box, okay, and start thinking about more revolutionary solutions to the sustainability problem. Here's one example. So storage is expected to grow exponentially. Storage requirements are going to grow exponentially in the next 5 years. So the amount of storage required, the expectation is that it's going to be significantly different than the amount of installed capacity that we have. So how do we deal with this problem? So in the book Worldwide Waste by Jerry McGovern, he noted that although storage is supposed to grow exponentially, we actually never access most of this information that we store away. 80% is never accessed, about 10% is only accessed for about 3 months, and the remaining 10% is frequently accessed. So one way we could think about this problem is that maybe we can develop some kind of AI or some kind of other algorithms to determine which data should be stored and which ones should not. Now let's assume even if we have a perfect predictor and customers are happy with the solution, we still are going to continue to have a problem maybe further down the road. It might not be in 2021 or 22, but it might be by 2030. So we need to think about additional solutions. And one such solution could be DNA storage. So the folks at Microsoft and University of Washington that have been working on DNA storage went back and looked at the sustainability impact of DNA storage and compared it to tape. And they looked at 3 metrics: greenhouse gas emissions, the energy consumption, and the water consumption. And they did a full life cycle analysis. And what they found is that DNA storage was 2.5 to 3 times more efficient in all these categories than tape storage would be. Now, the interesting thing is that when I talked to the authors, they said that when they first started with DNA storage, they really were not thinking about sustainability. They were thinking about it in other contexts. But in retrospect, it is also a really good sustainability solution. So this is how we can rethink components and how we can readdress that situation. But should we also rethink what it means to be a data center? Here's another example coming from Microsoft referred to as Project Natick, which is literally a data center in the ocean. So in Project Natick, they took 864 servers, they sealed them in a tank, filled it with nitrogen, and they deployed it 117 feet underwater in the North Sea. And then they brought it up 2 years later and looked at the characteristics of this data center. In fact, this was a working data center, with jobs submitted to it and so forth. While it was in the ocean, they had a lot of telemetry on this on the data center because they wanted to see if there were leaks or if there were security issues and so forth. So they also use that telemetry for AI for sustainability by tracking things like fish populations or ocean currents or ocean temperatures. When they brought it up 2 years later, They cleaned it off and looked at some of the characteristics, and they found some interesting things. The thing that they found that was really interesting was the components in the data center had 1/8 the failure rate of a similar cluster on land. Now, there could be a number of different reasons for this. It could be because it's a very tight operating envelope. I mean, they have a massive thermal sink in the North Sea. It could be because there was no humidity and the tank was filled with nitrogen. Or it could be because it was isolated and nobody was walking to the data center accidentally hitting something or loosening something up. Don't know yet, but it had some really interesting characteristics that we might be able to take advantage of. Now, that doesn't mean that you have to put all our data centers in the ocean. We can replicate some of these characteristics on land in other scenarios. And here's one such scenario, which is liquid immersed servers. So we can think about tanks where all our server components are immersed in liquid, at which point it can survive in the components can have significantly higher heat density because of liquid immersion. And we might be able to see similar reliability characteristics in these kinds of environments. So the bigger picture. In the last, I don't know, 30, 40 slides, I talked about data centers. I talked about carbon emissions from use and embodied carbon. We even looked at the carbon associated with the building infrastructures. But we really need to think about even a bigger picture when it comes to sustainability. I talked primarily about carbon, but we need to also think about water, reducing water use in the data centers, even things like restoring wetlands. As you saw, those data centers are enormous and they can really change the water composition of the area around there. We need to think about removing contaminants. In terms of waste, there are 56 million metric tons of e-waste generated every year. And this is not just data centers. This is e-waste for all components, from cell phones to laptops to TVs and so forth. And then finally, we need to think about electricity distribution. As I noted, renewable electricity is great, but it is inconsistent. So we really want to have 24/7 carbon-free electricity distribution. This can be achieved in some other ways, such as there's examples of research where they're looking at putting hydrogen tanks at the data centers such that when renewable energy goes down, they can use hydrogen as a backup source. So we talked about data centers. But the reality is we need to think about all electronic components as computer architects. So for instance, there are 275 million phones in the US, and if we can increase their use time from 28 months to 36 months, we can save about 1 million metric tons of carbon annually. And that's just 1 million metric tons in terms of embodied carbon, not even used carbon. Because if you look at numbers coming out of Apple, they have a carbon footprint of 25 million metric tons of carbon. But most of that, 74%, is manufacturing or embodied carbon. And only 19% of all of Apple's electronics, the carbon comes from use. So in addition, 1/3 of all the carbon in Apple comes from the manufacturing of integrated circuits. So what this means is that although I talked about data centers, I talked about sustainable silicon, we need to apply this problem to multiple areas. So one last thing I want to mention is let's really rethink what it means to be a data center and reimagine how we can build sustainable data centers. Now, as I noted earlier, DNA storage was a great solution, and because it used biomaterials. So Mother Nature, you could argue, has done a fantastic job on sustainability, much better than we as humans have done. So can we take these biomaterials that nature has improved over millennia and use them in how we think about building data centers? So we can think about green concrete or biofueled electricity, or even compostable electronics, such that we can throw the wooden PC board here into the compost heap once we're done with it. The ultimate indication of how well nature has done compared to how humans are doing is that the human brain runs on about 20 watts of power. When you compare that to the AIs and the amount of energy that AIs use, and not necessarily producing better results in the human brain, it's remarkable how well nature has done. And so we should think about how we can replicate similar behavior. So I'm going to leave you with a lovely picture of Seattle and the Space Needle. So this is my hometown, and a quote from Albert Einstein. So problems cannot be solved with the same mindset that created them. And so this is a call to action to the architecture community to rethink how we work with computer architecture in the world that we live in now, where we need to think about sustainability. So thank you very much. I do want to say that I want to acknowledge a number of different people from Microsoft, and I want to give a special shout out to Karen Strauss, who is my partner in crime on sustainable architecture at Microsoft. Also, if you are looking for materials, there are some websites listed here. This is just a starting point, and we'll try to increase the number of materials here. So questions? And thank you.
All right, Bobbie, thank you very much for this great and inspirational, at least to me, presentation. I know there are many things here that I've thought of before, but many that I have not. And, I thank you for, opening my mind a bit to some new things. We'll take questions now. We have a couple of sort of people who signed up ahead of time to ask questions live. So we'll start with them, and then I'll move on to moderating questions that are put onto the Q&A of Zoom. So
okay, sounds good.
Yeah. So Kamal, how about we start with you?
Hi, this is Kamal.
Hello, Kamal.
Hi. Now you haven't mentioned this in your talk, but one common way to reduce power in data center systems is to use ASIC designs instead of general purpose processors, dedicated ASIC designs to have dramatic reductions in power, essentially design the whole data system for power efficiency. But there are two difficulties. One is the NRE costs of making a new ASIC. The other difficulty is the intellectual difficulty or the lack of productivity in designing new ASIC designs. So what's your vision on the possibility of overcoming these two difficulties in using ASIC designs for power reduction?
Okay, so I think that when it comes to ASIC designs or specialized, I guess, accelerators, would that be another way of think about it?
Yes.
Is to think about how much they're going to be used. Now, people have been talking about accelerators for many years now. It makes sense when there is a high enough utilization rate and necessity for it. So if you think about, let's say, a very specialized data center that only addresses a particular problem, let's say such as, let's say search, then you can build specialized accelerators for that application stack. And then there'll be a guarantee that all the portions of the application stack will be able to utilize that accelerator. But if you're talking about a generalized data center such as Azure or let's say AWS, you have a mix of applications that can land in that data center, which means that you are building this accelerator, putting it in potentially on every single machine, but then only a subset of the machines are going to use it. So you are taking the NRE cost, you're taking the embodied carbon cost of this accelerator, and you have to weigh that against the potential for its utilization. And I think there is no single answer, but you have to kind of compare the two when you come up with that solution and determine whether it makes sense for your particular data center or application space.
Thank you.
All right. We have another person signed up ahead. Vinod, how about you go next?
Okay, am I audible?
Yes.
Yeah, thanks for the great talk. So I have two questions. First question is from a computer architecture standpoint, so what techniques, like going from general purpose to domain-specific architectures or out-of-order prefetching, what techniques contribute? Do you have any thoughts on what techniques contribute positively to reducing the carbon emissions? Should we be even thinking in such fine-grained manner? That's the first question. And the second question is, if yes, then how should hardware engineers reason about carbon emissions while designing systems, like they reason about performance, power, or other metrics that we usually do?
Okay. So there's a couple of papers out there that look at subcomponents of the architecture, such as, caches or branch predictors and the carbon emissions associated with it. So stepping back, there is a relationship between the area of the processor and the carbon emissions, okay? I don't have the exact numbers to say that it's a linear relationship or whatever. So if you can make the processor smaller, then it should have less embodied carbon emissions. And if you look at a processor and look at the area that's dedicated to components, what you see is that a significant portion of it is caches. So maybe by reducing the caches or pulling it away into another processor, another process node, we should be able to reduce the carbon emissions associated with that. Now that has to be balanced against the fact that it's in a different process node and you have to reach it and the performance implications of doing that. So once again, it's trade-off. So I can't give you exactly that solution X will work, but I think it makes sense to start looking inside the microarchitecture also.
Okay, we have a few questions also on the Q&A in Zoom. The first one is from Gustav Borgström, who asks, thanks you for the talk, and then asks if you have a prediction of how much energy data centers will use in upcoming years as a back projection.
In fact, if you look up online and say how much energy do data centers use now, you'll get like, I don't know, 4 or 5 different numbers depending on people's perception. So yeah, in the future, I think that renewables are going to continue to increase. Data centers, especially hyperscale, have these power purchase agreements such that we can continue to use renewables or encourage the utility to build renewable sources. That said, there's another problem that comes in with these scales. For instance, in Ireland, there are a number of data centers there that are being built by various different companies. And there's been a report out there that says by 2027, 1/3 of all power in Ireland is going to go to data centers. Now, that's non-sustainable. So there's this kind of mix and balance that goes in there. So honestly, I can't give you a prediction, but I got a feeling the power will go up because we've reduced it pretty significantly with all the efficiency improvements that we made. And really the only thing that we can do at this point is renewable sources.
Okay, all right, thank you. Another question from the Q&A. This is from Yashika Verma, who is asking whether there's a role for software solutions as well, since the focus was hardware, which makes sense for micro, but is there a role for software for the sustainable solutions?
Yeah, thank you for the question. Actually, I had a section in the paper that was titled No Good Deed Goes Unpunished, and how software folks have been getting lazy because processors have been getting so good. Now, that's a hardware perspective from me as a computer architect. But the materials that I'm showing here, the Microsoft devlogs with sustainable software, has a number of different ideas about sustainability and how we can think about software. But think about the fact that we basically have these interpretive languages. We don't recompile software a lot of times. And all these things that maybe make software easier to use will also lead to higher energy consumption. There are a number of papers out there, if you search on Bing or Google, that you can see that talk about software and the impact it has on sustainability.
Maybe a follow-up from this is also in a Q&A from Lahiru Rasayanke. Sorry for this name pronunciation, Rasyake, I guess, is asking if there's a way to sort of also include algorithmic benefits. Can you predict sort of or see what the algorithmic benefit is with respect to energy reduction? Asking if there's like a carbon emissions, like a Moore's law for sort of benefits you could get.
Absolutely, that could be another talk. So for instance, there in that same book, Worldwide Waste, there was a comment made about more people have climbed Mount Everest than have gone to the 10th page of a search result. Okay, so what that means is that when we think about generating these results, we can start thinking about how we design it such that we basically optimize for the most used case rather than optimizing for everything. If you search for climate change on Bing, you'll get something like 96 million results. Honestly, who in the world has time to go through 96 million results? So there is an enormous amount that I think can be done. And I would really encourage people to start looking into that area.
Another question from Q&A. I think we have time for one or two more.
Okay.
This is from Brian Schwedel, who's asking, what about energy storage? Could you, instead of shifting the computation in time or space, can you shift the energy in time?
Yes, a lot of data centers are now talking about, because we have these UPSs and such within the data centers. And so there is some research going on that say that maybe we can use the storage systems in the data centers, maybe expand them a little bit, such that we can use them as energy storage elements while to compensate for the variability in renewables. Um, and so there is research on that front. You can find a number of articles and such. Again, once again you search for them um, on Bing, and I would really encourage that. I think that that's a really interesting area, and also there are a number of fundamental political issues that come into the picture here because of if you want to sell back to a particular utility grid, how all those pieces work. There are politics and protocols involved with all of it. So really fascinating area.
Okay. Question from the HOVA interface, this time for a change.
Okay.
Should pricing in the data center reflect carbon costs? Should you encourage your customers and not just...
You know, right now, no, that is not how it's done, but it is an interesting analysis to do, because if you provide customers and if you tell customers, hey, if you lower your carbon intensity, we'll give you a cheaper price, then how is that going to change how customers are going to rotate to different data centers? For instance, they might pick the ones with the lowest carbon intensity, and that might cause problems for us because we have data centers in lots of different locations. But it's a really interesting problem, and I would love to see some modeling of all of this from an economic and a utilization perspective and so forth. I think it's really complex and it's really fun from an engineering perspective.
I'd like another question for Project Nautica. Did it affect the ocean life nearby with heat and or other things?
I haven't heard anything about it, but that's a good question. I don't think it really did. I think it was small enough such that it wasn't going to be a large heat source in that region. Obviously, very close to it, yes, but as you can see, there was a seal next to it looking very happy at the moment.
Maybe one, we have a couple more minutes, but I think we'll take there's one more question from Hova. And the question is with sort of a rebirth, I'll read it out, with the rebirth of IoT, maybe renewed trend for electrification, like more electric cars and things like that. Will that play a role in the sustainable architecture sort of as we move forward?
I'm trying to get a better understanding of the question. So are you talking about electric cars in terms of like AI for them in the local data centers, or?
So John Lee asked this question. I'm afraid I cannot clarify
No
this
problem.
question for you. I can take a guess, or I can put my spin on it. I
Sure,
would think
go
for
ahead.
IoT, if we really are to see 1 trillion devices or things of that sort, is the data center sustainability, let's say, for manufacturing relevant if you have sort of 1,000 times or 1,000,000 times more devices sort of deployed?
A good question. I think from a sustainability perspective, you need to think about all of it. Because with all these IoT devices, and especially if you want fast response times, we might not be able to use these hyperscale data centers. We might need to be physically closer to the location, kind of like the last mile situation, which means that we're going to have to put data centers in neighborhoods and other locations, which may not be as efficient. So I think it's a complex interaction. That doesn't mean that we should ignore data centers and just think about IoT, but there's certainly interactions between the two that we should consider.
Okay. So Bobbie, I think we'll end here.
Okay.
We're just on time. So thank you again very much for
Thank
a
you.
great talk. And I would have to say a very well handled Q&A session, despite the very varied questions that came.
No problem.
So thank you very much again. And
Thank you. It's been my pleasure.
and we'll stay all hopefully here in this session where we're on to the award session at this point.
Thank you, Matan. Bye-bye.